Hi everyone. For part 2 of 8.1, we're going to keep talking about the derivative of e to the x. And remember, since it is a nice simple derivative, it's just the derivative of e to the x is e to the x. What we're going to do is we're going to keep focusing on other types of things we can apply to it. So what I want to start with for today is the product rule and quotient rule from section 4.3. So product rule is for the derivative of a product. It's exactly what it says, and a product means two things multiplied together. So here's the product rule kind of as an equation, like basically copied straight out of a textbook. It's the derivative of f of x times g of x, two separate functions multiplied. And you get the derivative of f times g plus the derivative of g times f. Or I like to think of it as like a first function and a second function. I always say to myself, derivative of the first times second plus derivative of the second times first. Now the quotient rule is for derivative of a quotient. So instead of f times g, you have f over g. And it's a little bit more complicated looking. The way I presented it the first time through is I said that the part on top looks exactly like the product rule, but with a minus instead of a plus. Derivative of f times g minus the derivative of g times f. And then you have this extra part where the whole thing is over g squared, the bottom function squared. And again, this is how I kind of put it into words. I always say, this is what I say in my head as I'm doing it. The derivative of the top times the bottom minus the derivative of the bottom times the top, and the whole thing is over that bottom function squared. So let's do this. We're going to do one quick, easy example of each. On the left-hand side, we have the derivative of x times e to the x. That would be product rule. And on the right-hand side, we have the derivative of e to the x over x plus 1. That would be quotient rule. So let's do each one. So first of all, for the first one, once I notice its product rule, it's going to look like this. And I'm going to kind of set up a framework for the answer. And remember, this is the derivative of the first function, and this is the second. Not the derivative, just the second function. And this is the derivative of the second function times the first. So two of them you can fill in automatically. The second function is e to the x, the first function is x. So then you take the derivative of the first and second function separately, fill in your last little bubbles there, and then simplify. So the derivative of the first function was x, and the derivative of x is just 1. And the derivative of the second function, well, the second function is e to the x, and the derivative of e to the x is e to the x. So when you clean it up, 1 times e to the x is e to the x, and e to the x times x is exactly that. I would probably put the x in front, although you don't have to. And that's fine for an answer. One thing you can do is factor the e to the x out and make it e to the x times 1 plus x. That's your cleanest answer. And that's the one when we get to, if you ever have to like solve for x, you would have to do that anyway. So it's a good habit to get into. But basically, that's a quick review of product rule. And now on the right-hand side, let's do quotient rule. So for quotient rule, I'm going to set it up kind of the same way as I did the last one. I'm going to do my 4 bubbles with a minus in between this time. And the whole thing is going to be over something squared. So just for the notes this one time, I'll say this is the derivative of the top. This is the bottom function. This one is the derivative of the bottom times the top. And this is going to be that bottom function right there. So 3 of our bubbles you can fill in automatically. The x plus 1 goes here and here, the bottom function, and the e to the x goes here. So the only thing you have to do, just like on product rule, is fill in those last 2 bubbles by taking the derivative of the top and bottom separately and making sure you have everything in the right place. So the derivative of the top function is e to the x. Remember, the derivative of e to the x is e to the x. That's our easiest derivative to take. And then for the derivative of the bottom function, you actually just get 1. The derivative of x is 1. and the derivative of 1 is 0. So if we clean this up, I'm going to get rid of me for a minute. If we clean this up, let's do this. Let's distribute the e to the x on that first part. E to the x times x is x e to the x, and e to the x times 1 is e to the x. And then for the second one, you have minus 1 times e to the x. That would be minus e to the x. And it's all over x plus 1 squared. Now, because we distributed, we can see the e to the x minus e to the x cancels out. So for my final answer here, I have x e to the x over x plus 1 squared. So that was kind of a simple example of each one, a simple example of product rule and a simple example of quotient rule. And by simple, I mean I just put an e to the x in there. I didn't involve also having chain rule or anything like that. All right, I want to do one more example, a little bit more complex one this time. So let's do the derivative of f of x equals x plus e to the 3x squared all over e to the x. Now this is definitely a quotient rule question again. I'm not going to fill in the bubbles and write out like derivative of top. I did that once for the notes. For now on, I'm just going to do the question. So when I go find f prime, once I realize it's a quotient rule question, I always draw myself like this big fraction to work with. And the first thing I do is I take the bottom and I square it. E to the x squared. And then it's derivative of the top. That one, you know what? I think I'm going to do that one off to the side. I'm going to leave a space for it now. Derivative of the top times the bottom, which is e to the x, minus the derivative of the bottom, which is also e to the x, times the top, which is x plus e to the 3x squared. All right, so I left that first one blank because I can tell there's a chain rule involved in there, and I don't like to get my work too mixed up. I'm going to go off and do that one off to the side. So I'm going to do the derivative of the top, which is x plus e to the 3x squared. Okay, the derivative of x is 1, and for the second one, it's a chain rule. The derivative of e to the 3x squared is, well, it starts off with anyways, with 3x squared, but then you have to chain rule. You have to multiply by the derivative of 3x squared, and that's power rule. So you multiply 2 times 3 is 6, you lower it to x to the first power, and what we get is 1 plus 6x e to the 3x squared. So maybe you can kind of see why I didn't want to try and squeeze all that work into a problem that I was already doing. I like doing that off to the side, then I can go back to my problem and just put that in. 1 plus 6x e to the 3x squared. Okay, now, before I go to clean up this question, what I notice is I have an e to the x here and an e to the x here. That's a common term that can be factored out on top, and once it's factored out on top, it can actually be canceled with one of the e to the x's on the bottom. So let's do that. It's good to look for things like that. And this happens a lot with the e to the x derivatives because it is its own derivative. So you end up with multiple e to the x's in your answer, and you can sometimes factor them out and cancel them. So let's factor that e to the x out on top. And what it would leave me with is 1 plus 6x e to the 3x squared minus x plus e to the 3x squared. And now remember, once you do that, we have an e to the x being squared on the bottom. That's like e to the x times e to the x. That e to the x that you factored out will cancel out with one of those on the bottom. And for my final answer here, I don't think I have any common terms on top. So let's just say 1 plus 6x e to the 3x squared minus x minus e to the 3x squared. Remember, I distributed that negative, so they are both negative on the last two terms. And the whole thing is now over just e to the x. And that's my final answer. That's as clean as I can make it. There's no more common terms, nothing else to factor out. But basically, I did a quotient rule with a chain rule involved also. That's the work in yellow off to the side. And then I did some cleanup work where I noticed I had a common term in e to the x that could be factored out and canceled. All right, so that's our review of product rule and quotient rule, and also how it can be how it looks when there's e to the x's involved. We have one last piece I want to add for today, and that's implicit differentiation. So this is from section 4.5, and implicit differentiation is basically when you have x's and y's mixed together. Instead of just y equals a function of x, you have one equation where the x's and y's are all jumbled up. You might have more than one y in your problem, things like that. And we're differentiating, we're taking the derivative with respect to x. Oh, that went backwards for some reason. So that's what I was saying a second ago. For equations that are just not written as y equals a function of x, we are going to differentiate with respect to x. And what that means is any x term, just take the derivative of normally. Any y term, you take the derivative of, but you end up with a dy dx on the end. And you'll see when we do the example, you'll remember, I'm sure. And then basically, once you've done that, you solve for dy dx. And you might remember from the first time we did this, it's very common in this question for you to end up with 2 or 3 different dy dx's in your answer. You have to group them together, factor it out. That's how you turn more than one of something into one of something, and then finish solving. So let's do an example, and I think you guys will remember how to do this question. So this is what an implicit differentiation question looks like quite often. You have more than one y in the problem. You have an e to the y on one side, you have a y on the other side, everything's all jumbled together. So I'm going to take the derivative implicitly, and I'm going to start with this first piece right here, this first term. Now I want you to notice right off the bat, that's product rule. That's e to the y, my first function, times x, my second function. So it's going to be derivative of the first times second plus derivative of the second times first. Okay, derivative of the first function. Now we have an e to the y instead of an e to the x. But remember, when you're taking derivative of e to any power, the first part of your answer is always the same thing. So the derivative of e to the y is e to the y. But remember, when you're doing it implicitly, when it's a y instead of an x, you get a dy dx in there. So the derivative of e to the y implicitly, or with respect to x, is e to the y times dy dx, basically. Okay, that's the derivative of the first times the second, which is x, plus derivative of the second. Derivative of x is just 1. Remember, when you're doing implicit, if you get an x term, just take the derivative normally. That should be the easy part. And then that's times the first function, which is e to the y. And we're done with that first one. Okay, now the second one, the derivative of 3x squared, that's an easy one. That's just normal. It's power rule. Multiply by 2, you get 6. Oops, not equals, plus. Multiply 2 times 3, you get 6. Lower the power by 1, so you get 6x to the first, or 6x. And then your last derivative over here is y. And remember, when you're taking the derivative of a y term, you take the derivative, like the derivative of y is 1. But because it was a y instead of an x, you get that dy dx in there. So if I clean this up a little, I did it by color just to match it up piece by piece. But if I clean this up a little bit, the first one, if I stick everything together, I have x e to the y dy dx plus e to the y plus 6x equals, and you could put dy dx. I'm going to leave the 1 there, and you'll see why in a second. I'm going to leave the 1 and call it 1 dy dx. So basically, if you're looking at your dy dx terms, I have 1 here, and 1 here. Now, whenever you have more than one, this is what I was talking about earlier, you want to group them together and factor it out. So I think I will leave everything and basically just move that first term. I'm going to subtract x e to the y dy dx from each side to cancel it out. And what I get is e to the y plus 6x equals 1 dy dx minus x e to the y dy dx. And I'm running out of space. I'm going to have to kind of try to squeeze it in on the right over there. But basically, once you've done that, you want to kind of think of this as a group and factor the dy dx out. So for my next step, what I would have, I will leave the e to the y plus 6x, factor out the dy dx, and that leaves me with 1 minus x e to the y. And then once you've factored out the dy dx, divide by whatever was left over after you factored, and that should be your final answer. So if I divide both sides by 1 minus x e to the y, to cancel that out, this thing here, I barely squeezed it in there, that thing there is your final answer. So dy dx for this one ends up being e to the y plus 6x over 1 minus x e to the y. But the important thing is that you remember the steps. So if you look at it, number one is taking the derivative implicitly, and that's where you have to really look at the difference between the x terms and the y terms. But then there's a second part to this question where you still have to find dy dx. You don't just take the derivative and you're done. You have to find dy dx, because that's what I asked you to do. If you look at the directions, that's exactly what you're asked to do, is find dy dx. Well, that's what we did. We solved for or found dy dx. So you have the second part of this question. After you've taken the derivative, if there's more than one dy dx, you got to get them all grouped together and factor it out and divide, and then what's left over will be the answer to the question.